our lesson today, we are going to talk about slope with linear lines, specifically also looking at how we can write a linear equation. We're also going to chat about the differences and similarities between slope and the average rate of change. The average rate of change is directly correlated to the difference quotient that we talked about in our last unit. When we talk about a line on a plane, we know that there has to be two distinct points on that plane to determine that particular unique line that has those points. In order to understand and get a sense of steepness, whether we have a positive or negative slope, we need to determine what the slope equation is. When we have 2 points, we can find the slope by taking the difference of the y values over the difference in the x values. This can be described as the ratio of the rise over the run or the fall over the run, but we're always running to the right. We're never running backwards. We're always moving forwards. We also know that slope is constant throughout, so that we will always rise a certain amount and run a certain amount, or fall a certain amount and run that same amount no matter what. We know that if the slope is positive, our line is increasing. If it is negative, it is decreasing. And a line that has a horizontal line is a slope of 0. And our vertical lines are undefined slopes. Because we can't, thinking of driving a car, we can drive a car on a increasing line, a decreasing line, a slope of 0, but we can't drive a car on a vertical line. That would be pretty dangerous. So let's start off by finding the slope of a couple of points. It doesn't matter which point you describe as point, the first point or the second point, just as long as you're consistent throughout. I'm going to label the first one as x sub 1, y sub 1, and q as x sub 2, y sub 2. When I'm finding the slope then, I'm going to take the difference in my y values over the difference of my x values. And in this case, we'll have 4 minus 2 over 3 minus a negative 1. Most of you could probably do this in your head, but our slope is 1/2. So we would rise 1 unit, and then we would run to the right 2 units. And this would be a pattern that would go over and over and over again. Moving to our second slide, we're going to talk about the rate of change with respect to the average rate of change. So using more formal notation, this triangle is known as delta, and delta means to change in Greek lettering here. So it's the change in y is the difference of our y values, and the change in x is the difference in our x values. We can write the slope as the change in y over the change in x, which can describe the slope. Now when I'm looking at a particular function, we can see on the right-hand side that sometimes we're not always dealing with nice, straight, linear lines. Sometimes we have curvy lines, and we need to find what those rates are. So when we're looking at the secant line, which we talked about with the difference quotient, it was looking at this slope between 2 points. Finding that equation is what we did in the last section. There's always going to be a specific interval that we're looking at to find that average rate of change, an interval that is included. And when we find that interval, we can define the average rate of change as taking, evaluating the function at the last interval minus evaluating the function at the beginning of the interval, all over the difference in the interval values. This particular slope then is directly tied to the secant line. Let's look at slide 3. Using data from the Bureau of Transportation Statistics, the average fuel economy in miles per gallon for passenger cars in the U.S. can be modeled by f of t is equal to a lot of decimals on the interval between 0 and 28 included, because they have less than or equal to signs, where t is the number of years since 1980. So the interval we have is 0 and 28, and where 0 represents 1980, and 28 represents 28 years after 1980 itself. So that would be 2008. Find and interpret the average rate of change. So we're looking at what is the slope when time is 0 and when time is 28. So I created two x values to kind of get a visual utilizing decimals, and I also put our equation here so we could see. I'm looking for what is the slope of this particular line. So what is the average rate of change? That is our clue to utilize the formula from the previous page when it's asking us to find that average rate of change. We need to find the change in f over the change in time for years. That's equal to f of 28 minus f of 0 all over the interval, the difference of the interval. This then gives us, when we substitute 28 into our formula here, a pretty ugly decimal number. So I would definitely expect you to utilize a calculator to help us evaluate each one of these for accuracy. You don't have to do that by hand. Substituting in wherever I saw x, I substituted, or t, excuse me, I substituted in 28 minus, and this is a nice one because there's a lot of zeros, times 0 squared plus 0.45 times 0, which is 0 plus 16. And this is all over 28 minus 0, which is 28. Utilizing a calculator then, the change in F, so the change in the fuel economy over the number of years, over the change in the number of years, is a pretty interesting decimal, 0.2372. So that's our slope. And it shouldn't surprise us that we would get a decimal looking at all the ugly decimals that we started with. So to interpret us, this tells us that during the years, (1980) to 2008, those 28 years, the average fuel economy of passenger cars in the US increased. Again, we have a positive value, so increased by a rate of 0.2372 miles per year. And I know that it's per year because we're dividing by the number of years. So we divided the fuel economy by the number of years. I should say per gallon per year, excuse me. Now this would change ultimately if we were to look at the slope between 0 and 10 years, our slope would be much steeper. So that's why we call it the average rate of change, because that slope is going to differentiate depending upon the value of the years in which we are looking at. In our next example here, the temperature T in degrees Fahrenheit, T hours after 6 a.m. is given by our function. Find and interpret what is the temperature at 4 hours after 6 a.m. and 8 hours after 6 a.m. My red line here represents my function T of T. My purple line here represents when T is, or little t I should say, little t is 8 hours, and my green line represents when time is 4 hours. So here and here. Let's find and interpret them. So first of all, we can easily substitute 4 in and evaluate. T of 4 then is negative 1/2 times 4 squared plus 8 times 4 plus 32. When we simplify, we get 56. This means then that when the time is 10 a.m., which is 4 hours after 6 a.m., the temp is 56 degrees. Similarly, let's evaluate when time is 8 hours after 6 a.m., so T of 8, negative 1/2 times 8 squared plus 8 times 8 plus 32 gives us 64. This time, when the time is now 2 p.m., which is 8 hours after 6 a.m., the temp is 64 degrees. The slope between when time is 4 hours and 8 hours after would be a positive slope. However, if I were to look at the temperature between 8 a.m. or looking at the temperature between 8 hours and let's say 12 hours, we have a downward slope. So identifying the different intervals will be important to interpreting what we're looking at. So let's go to the next page. We'll take this one step further now that we evaluated. Now it says find and interpret the average rate of change with the temperature over those 4 specific hours between 4 hours after 6 a.m. and 8 hours after 6 a.m. Again, I still have my same graph. I'm using Desmos to help me verify some of this information. So when I'm looking at 4 hours and 8 hours, we can expect that there should be an increase over time. So the change of the temperature over the change in time, we need the temperature evaluated at 8 hours minus the temperature evaluated at 4 hours, all over the difference of those hours themselves. And we just so happen to have found that on the previous page. So 64 minus 56 was the evaluated points over 4. This is 2. What does this tell us then? What is the interpretation? So between 10 a.m. and 2 p.m., the temperature increases, because it's a positive 2, increases, and our slope is positive, on average. Notice I'm using the word on average because I'm finding the average rate of change at a rate of 2 degrees per hour. And I know it's per hour because we are dividing by those hours. Now it says find and interpret the average rate of change between 8 hours and 12 hours after. So now we were looking for 8 hours, and this line is 12 hours. So we need to identify what this value is. 12 what? And we already know that this is 864. Again, we're looking for the change in temperature over the change in time on a specific interval between 8 and 12. I need to evaluate T of 12. We already have T of 8. We found that on the previous page, over 12 minus 8. I'll let you evaluate. I know you know how to evaluate, so I'll skip that step. Stop! Go! This will give us 56 minus 64 over 12 minus 8, or 4. which reduces to -2. So this time we have a negative result. This tells us then between 2 p.m. and 6 p.m., since 6 p.m. is 12 hours after 6 a.m., this time the temp decreases, and it shouldn't surprise us, we visually can see that it's a negative slope, decreases on average at a rate of 2 degrees per hour. On our next slide here, we talk about the constant rate of change, which means that the object is moving with a constant velocity and our curve is linear. So the typical slope that we've been using, where the slope is the same, directly correlated to y equals mx plus b. Y equals mx plus b is when we have a constant rate of change. We are always rising 1, running 2, rising 1, running 2. This remains the same throughout the entire linear line. However, the average rate of change is what we are finding when we're finding the slope of the secant line, which is what we just found, again, directly correlated to the difference quotient. Depending upon the 2 points that we have, we're not going to have that same line for every 2 points. The slopes will be different depending upon the points that we choose, just as we saw in the last example. If we are looking for a specific instantaneous rate of change, not over a period of time, but at a specific point in time, the instantaneous rate of change is what we cover in calculus. The instantaneous rate of change is the specific tangent line. So let's say that it takes us 2 hours to travel 100 miles. Our average speed over those 2 hours would be 50 miles per hour. However, we do know that when we're traveling, sometimes we speed up, sometimes we slow down, sometimes we remain constant. So depending upon a specific point in time in my travel, I'm going to have an instantaneous rate of change. At one specific point, I might be going 25 miles an hour. So even though I might speed up or slow down, depending upon the time I specifically am looking at, there's going to be a 1 instant rate of time or change at that time. Whereas the secant line tells us on average how fast we are going over the entirety of our trip. The next slides will take us back to slope. When we're looking at slope-intercept form, if I'm going to find identify and write the equation in slope-intercept form. Now, I know some of you might prefer point slope form. We are going to talk about that, but you should be able to utilize both slope-intercept form and point slope form here in a second. When I'm looking for slope-intercept form, there's 2 things that we need. We need to know what the slope is, and we need to know what the y-intercept is. We need the y-intercept and the slope to write our equation. So find the slope-intercept form with the line if we have a slope of -1 and we have a specific point. Well, I know my specific point, I'm given an x and a y value. I have my m value, but I don't know what my y-intercept is. I don't know what that y-intercept is. But what I can do is substitute all of the things that I do know into the generic equation and solve for b. I know that a y value on this point is -7 is equal to my slope of -1 times my x value that I have of -1 plus b. So y equals mx plus b. Notice the only variable that's left is the b variable, so I will solve for b. -7 equals 1 plus b. So -8 is b. Now that I have my slope and I have my y-intercept, we can certainly write the generic form of our equation. Y equals -1x minus 8, or You don't have to have that -1, y equals -x minus 8. Slide 8, looking at point slope form. In order to use point slope form, we need a slope and a point. It doesn't matter what point, we just need a slope and a point. Write the equation of the line that contains 2 points, and we're going to write it in point slope form. We don't have slope, but we can find slope because we know we can find the slope by using our equation, the difference of our y values over the difference of our x values. So let's find our slope first. So I'm going to let this be x sub 1, y sub 1, x sub 2, y sub 2. So my slope is going to be 1 minus 3, the difference. My slope is going to be 1 minus 3, the difference of our y values over the difference in our x values, 2 minus a -1, or -2/3. Now that I have my slope, I just need to choose one of my points. Doesn't matter which point you choose. For simplicity, I'll just choose my first point and substitute it into y minus the y value, and one point that I choose is equal to -2/3, the slope, x minus the x value, so x minus -1. So when looking at the equation, I have y minus a y value point equal to our slope times x minus the x value. And now we just simplify a little bit here. Y minus 3 is equal to -2/3, x plus 1. And we could simplify by just getting y by itself. Y is equal to -2/3 times x plus 1 plus 3. And now it's also written in the transformation formula, so we could identify if we are shifting left, we are shifting up, and then we can also look at reflections and scaling as well. The last slide puts things into perspective for us with respect to a word problem and writing it within a piecewise function. Just some notes on linear lines with constant functions. We know that the linear line function is mx plus b. The domain, when we're looking at a linear line, is all real numbers because it continues left and right forever and ever. Also, if we have a constant function or a horizontal line, yes, we are still going left and right forever and ever, but our range is just the value itself. So if we have this function as y is 5 or f of x is 5, we would have a horizontal line at y equals 5. The domain would still be all real numbers, but our range is just going to be 5 because no matter what I choose for x, our y will always be 5. And our last example, a local pizza store offers medium 2-topping pizzas delivered for $6 per pizza, plus a $1.50 delivery charge per order. On weekends, the store runs a game day special. If 6 or more medium 2-topping pizzas are ordered, they are $5.50 each and no delivery charge. Write a piecewise defined function which calculates the cost in dollars of p medium 2-topping pizzas delivered during a weekend. So let's say I wanted to find what is the cost, just to kind of understand the problem, of 5 pizzas. So it says if I have 6 or more, I have one function, but if I have less than that, I have a different one. So if I had 5 pizzas, it's going to cost us $6 times those 5 pizzas plus the $1.50 delivery charge to give us $31.50. That would be the total. But let's say I order 7 pizzas. Let's do 7 pizzas, just 2 more. How is this going to change what it will cost us? Well, not only do I get charged $5.50 per pizza, but now I have no delivery charge. So $5.50 times 7 pizzas plus 0 delivery charge. So $38.50. So let's try to write the piecewise function. So the cost per pizza is equivalent to, well, when I had less than 6 pizzas but greater than 0 pizzas, it would cost me $6 times the pizza, how many pizzas, plus $1.50 for delivery. So the equation would be 6 times P plus $1.50 when we have the value of pizzas between 0, the number of pizzas, and less than or equal to 5. So when we have 5 or less pizzas, and of course it makes sense that 0 would have to be pizzas would have to be greater than 0, because ideally you're not going to order 0 pizzas, because then there would be no order and it would make no sense to utilize this. So we'd have to at least order 1 pizza, right? So this also could be 1 greater than or equal to, etc. That would be another appropriate part. The other part happens when we have 6 or more pizzas. Then it would cost us $5.50 per pizza when the number of pizzas we order is greater than or equal to 6 pizzas. So now we have just written a piecewise function for the number of pizzas that we are ordering. And this concludes our lesson for 2.1.